Nice. So next speaker is Adrian Fiorucci, and we'll talk about, let me see, leaky boundary conditions in ADS spacetimes.
Okay, so thank you for giving me the opportunity to talk today. So for those among us that don't know me, this is a very short biopic. So in physics and mathematics in Belgium. I made my PhD in Brussels under the supervision of Geoffrey Compère and Glenn Barnish. And I am currently a postdoc researcher at the Technische Universität Wien in Daniel Grumiller's group. So my main research interests are theoretical aspects of gravitational wave physics, on which I will talk more precisely today. More generally in asymptotic symmetries in gauge theory, more precisely BMS symmetries in gravity and stuff like that, of radiative and open gauge system, and also bottom-up approach, holography and flat holography. So studying theoretical aspects of gravitational wave physics is nowadays a very trendy topic, mainly thanks to the fact that the LIGO collaboration 1 century after the Einstein prediction, and thanks to some encouraging previous results, namely by Hulse-Taylor in indirect detection of gravitational waves, finally managed to detect directly gravitational some black hole merging. That opens a new era of gravitational astronomy and gives rise to the ultimate test for activity. So the phenomenology of gravitational waves can be encapsulated in flux balance laws at null infinity of the relativistic spacetimes. These flux balance laws holds for the charges related to the so-called asymptotic symmetries. We want some flux balance laws which encodes the loss of energy or angular momentum. If you want to encapsulate this type of solutions in your phase space, you want to study some kind of leaky boundary condition that allow for some symplectic flux through the boundary. The boundary is thus permeable, which leads to some kind of non-equilibrium physics. Hence, you don't expect to conserved or integrable charges. For the holographic perspective, you will have a kind of sourced holography, since the gravitational the physical sources for your dual quantum theory. So you are seeking for leaky boundary conditions in general relativity, which is something very natural from the asymptotically flat perspective. You know all the BMS stuff and the fact that the conservations of the BMS charges the going out of your spacetime. In the presence of a positive cosmological constant, in order to don't impose so much constraints on the Cauchy problem, as you can see on this Penrose diagram, it is also essential to consider leaky boundary conditions. When the cosmological constant is negative, the situation is very different because conservative boundary conditions are more widely discussed in the literature since well suited for holography. However, what I want to stress today is that leaky boundary conditions in such a context are very appealing because they are more natural from a gravitational wave perspective. They are needed, for instance, in recent discussions on black hole evaporation, namely the program. And they induce some kind of non-equilibrium holography, which will give a promising route towards a 4D, 3D conception of flat holography, if you can get somehow the full control on a notion of flat limit. So in my poster, I will discuss a bit more later the Lambda BMS research program, which came from this kind of reflections with my advisor, Geoffrey Compère, and my friend, Romain Ruzziconi, who is there today. And the main upshot I want to stress is that the asymptotic of asymptotically ADS spacetimes is the Lambda BMS algebroid in the following sense, because this group, which is more detailed in the poster, whose concentration, whose relation are there. All the charges for this asymptotic group reproduce all the needed flux balance laws to discuss practical experiences with gravitational waves in that context. The lambda BMS algebroid contracts into the well-celebrated BMS algebra in the flat limit. And finally, the lambda BMS phase space reduces to the standard asymptotically flat phase space in the flat limit. So more details are in my poster, and on related topics, I advise you to give a careful attention to Laura's lecture and Romain's presentation, which will talk about BMS, so again, but in celestialography. Thank you, buon Natale a tutti, mille grazie.
Okay, thank you very much for the talk and also for the Christmas wishes.
Thanks.
Okay, are there any questions? So you say that your formalism is suitable both for de Sitter and anti-de Sitter.
Exactly.
Which kind of like, what is the main difference that you have in the last formula that you showed there? Like in the last two? Can you define a bit? No.
No.
This psi, what is? Can you explain a bit more?
Okay. I not so much time to explain. So this psi is in fact a boundary diffeomorphism. So it's on the conformal boundary of de Sitter or anti-de Sitter. And you see that the peculiarity here is that these vectors do not form a genuine algebra, but rather an algebroid, because they depend, because of the presence of the cosmological constant, they depend on the field. This is the boundary metric, in fact. This is some components, at least, of the boundary metric. So that explains that you will need a notion of Lie algebroid rather than a Lie algebra. Okay.
So the form is the same, it's just the
exactly.
sign of the cosmological constant.
Yes, but I want to stress that this is the present of the cosmological constant that imposes this coupling with the field, in fact, which disappear at the flat limit and reproduce the standard BMS algebra.
Okay. So the only difference is that term.
Okay. Afterwards, you have a lot of physical differences because of this Penrose diagram, but I can discuss about that a bit more in the poster session. If you want.
Okay, sounds good. Okay, yes. Any other questions? Okay, if not, let's give it another round of applause.
Thanks.